Thanks everyone for joining this morning. Hope you have your coffee. I've actually already finished my coffee for the day, so I don't have a mug in hand, but I'm energized and ready to go for the day. So as Ed mentioned earlier, one of our recent product releases this year was the SRM 100A, which is a new and improved revision to the SRM 100. And because we have this new product, this new revision, wanted to take an opportunity to talk about some of the theory behind it and why it exists, what it does, and that kind of thing, so that you can make a more informed buying decision if this is a product that you need for what you're doing out in the field. So I'm going to talk about soil resistivity and pH measurement, specifically how it relates to corrosion in the corrosion industry. So to start off, let's talk about the difference between resistance and resistivity. They're very similar, but we're speaking to resistivity, and resistance is the more common, common property for materials, and really what that's referring to is the opposition of the flow of electricity through something, through a resistor, through a wire, through just some material, and it's the magnitude of its ohms dictates how easily or how difficult it is for electricity to flow through it. Resistivity is very similar to resistance, but it ends up being, you could almost think of it as like an average, and what it is kind of talking about with respect to materials, kind of the average resistance across or through the body of that material. And this is the more appropriate measurement that we use for soil, because the soil conditions around a pipeline or some other oil and gas asset can change dramatically depending on where you are. And so it's good to get an average resistance through that soil, since it's not kind of a homogeneous type of material. And the SI unit for resistivity is the ohm meter, of course, indicating the resistance across a length of that material. And the symbol that you typically see for resistivity is the Greek letter rho, which looks like a lowercase kind of soft p. So why is soil resistivity important? Well, soil resistivity is very influential on the corrosivity of an environment where, like, a pipeline might be buried. And in general, low resistivity corresponds to high corrosivity. I'll get that at least once during the virtual brew here. And high resistivity corresponds to low corrosivity. And this is an essential measurement to take when a CP system is being designed, or if you're evaluating kind of the long-term changes and progression of a CP system or the environment in which it's installed. So for a high resistivity environment, it's going to take more power, more energy to pump current through that environment. And so, typically a more expensive CP source or ground bed would be used. A low resistivity means that electricity, electrons are going to flow much more readily. And so you're going to be more susceptible to faster corrosion. This table here, soil resistivity and the corrosivity rating is, I think we pulled this from some of the AMP standards and documentation, but just generally speaking, this is what one could expect in terms of the soil resistivity measurement. In the world of CP or corrosion, you typically see ohm centimeter. Ohm meter is the SI kind of standard unit for it, but we typically will measure it in ohm centimeters, and this is related to the probes that we use. They're generally in the order of centimeters in size, as opposed to something that would be meters in size. And I'm trying to get my button working here. Oop. Go back. All right. As I mentioned, soil resistivity can vary pretty widely depending on where you are. And location is local, so it could be from across the room to where I am right now. Soil resistivity can vary, or more dramatically, different parts of the country have soil resistivity just based upon the characteristics of the environment, the weather, and so forth. And it changes seasonally. For rainier seasons in an area, your soil resistivity is going to be lower because you now have added moisture into the soil that's going to conduct electricity better. It's affected also by electrolytes, other minerals, and how those interact with the moisture in the soil. Temperature, because if your soil is frozen, it's going to be in more opposition to the flow of electrons. The soil type and the level of compaction. If you have a lot of rocks, as opposed to sand or other more compact soil, that's going to affect your soil resistivity as well. The more compaction, the lower the resistivity, because all of those rocks and all the all the atoms and everything are going to be in closer contact with one another to allow for that electricity to flow easier. Now, there's a whole variety of methods that can be used to measure soil resistivity or resistivity in general. The ones that are typically used for the corrosion industry are the ones that I mentioned here. And there's no method that's better than another. It really just depends on what the use case is, what you're trying to get out of your reading. But I wanted to mention kind of the three major ones, and then relate them to the product that we have, the SRM100A. So the 4-pin Wenner method we'll go through is one of the more common ones that's out there, and then the soil box method and the single probe method. So in the 4-pin method, what happens is you're literally placing 4 probe pins in the ground, and this is typically a measurement that's taken over a very large surface area. And a lot of times this measurement will be taken prior to a dig, prior to installing the structure or even the CP system, because it can be used to get a general idea of what the soil resistivity conditions are in an area for the use of designing the CP system, or establishing what materials you want to maybe put around a pipeline, what kind of gravel or sand or whatever you might want to put around the pipeline. And so what's really neat about this method is the spacing of those pins has a direct correlation with the depth of the soil. So say, for example, you space the pins 6 feet apart, your resistivity measurement that you end up getting can be correlated to what it might look like 6 feet below the surface of the earth. And so, you can space those pins accordingly for how deep you're going to be burying the pipeline. And I've got 2 different kind of methods here. One uses a galvanometer and one uses the separate voltmeter and ammeters. But at the end of the day, a galvanometer is doing the function of the voltmeter and ammeter just kind of in one box, where you have a stimulus current that's being generated and flows through the earth, and the voltage drop from the flow of that current, that stimulus current, is measured, and that's all converted to the resistance, the spacing of the pins, and so then you can convert that to resistivity. Another method that's used, and I would call this more of the lab setting type of method, is the soil box method. And really, this is identical to the 4-pin Wenner method in the theory or the methodology behind it. You're just obtaining a soil sample and putting in this kind of controlled box condition and measuring the resistivity. And so this is important for maybe you want to evaluate, like there's been a corrosion incident, or you want to you've done a dig and you want to take a soil sample and measure that in a lab later on. You can take that soil sample, send it to a lab that might do this, or you might have the gear yourself to conduct this measurement and get a soil resistivity measurement. I will say that one disadvantage to doing this type of measurement is that you lose the variable or you influence the variable of soil compaction on that resistivity measurement, because the moment you dig up the soil and put it into this box, the compaction between what's in the earth and what's in this box are going to differ. And so that variable will come into play. And you just have to keep that in mind when you're using this information to make decisions about how you want to alter your CP system or alter the conditions that are around the structure. The third method is the single probe method, and really it uses the same methodology as the previous two methods, where you have a stimulus current that's generated and the voltage drop is measured across the path that stimulus current is flowing. The difference here is that you don't have pins that are spaced out far apart, and you don't have pins that are spaced out within a box. You now have a couple of probe terminals that are located at the end of this metal rod, and the current will flow. And like I have an example here from our SRM 100A system. This is our short probe, and at the bottom of this rod, there's a number of probe materials. A couple of these metal probe materials at the end are where the current will flow from one to the other, and then the voltage is simultaneously measured across those. And so you're getting a very localized reading of resistivity when you use this method. And this method in particular is very useful if a dig has been conducted and you want to get into the hole and measure the soil resistivity conditions around the pipeline. I've heard, and we generally recommend I've heard from technicians and engineers who do this in the field, and we recommend taking multiple samples like around your structure and then getting an average of those, because from the top of the pipeline to the bottom to the left and the right, even the soil resistivity can vary based on the location around a single section of the pipeline. And so it's a good idea to get multiple measurements and then average those out to get a general idea of what the soil resistivity conditions are like. And so this is an example of the bell hole probe. Yeah, was there?
Yeah, on the previous slide, Gord asked, can you please address how the depth of the pins affects things? I think on the single probe method, you've said, look, it's a very localized thing.
Yeah.
It's just going to give you the soil resistivity right around the probe itself. What about on the
so because you're taking a sample of soil away from the environment, the spacing of the pins here is fixed and is really used for the calculation of the soil resistivity. It doesn't have a bearing on the depth of where your structure is. So if you took your sample at the depth of the pipeline, then you could get a general idea of what the soil resistivity is at that depth.
He's asking about the depth of the pins themselves, not the box.
Oh, it's really from my experience, it's really kind of a negligible thing, because the pin links and their depths, you really want to just get it deep enough that it's going to stay in place. But the depth that you're generally trying to get a sense of the average soil resistivity is much larger than, say, the depth that the pin is going into the ground. You want to get it into the ground far enough that you make good contact with the soil. You want to get through kind of the upper layers. If you're just kind of penetrating through mulch or grass and kind of the topsoil, and you're not really getting to the meat of the soil, then your reading won't be as accurate. So you want to get down to that area where the soil is more representative of what's going to be around the structure. Does that answer the question?
Yeah. I think he was asking about the Wenner method, right? Yeah. So I think you just answered that. We're just not on the right slide. Yeah.
All right. I think I covered everything here. So the previous method is what I would consider to be kind of the lab method or lab accurate, whereas the single probe method with regards to resistivity is more the field method, field accurate type method. So now let's shift gears and talk about pH. So pH, generally speaking, is a measure of the acidity or the alkalinity of a solution. And the corrosiveness of a material and its pH really depends on what the material is. So for steel and iron, which we're commonly up against when we're looking at the structures for oil and gas pipelines, as you get more acidic, it becomes a more corrosive condition, and as you get more basic, it's less corrosive, or in according to the kind of the chart that we've shown here, you're not experiencing really any corrosive condition once you get above a pH of about 10. And so this is again another variable that's important to measure when you're either preparing to bury a structure, or you're evaluating the conditions around a structure during a dig or, at some point during the life cycle of that structure. And much like resistivity, the location plays a huge part in the pH that you're generally going to experience. In these maps, I guess on the left side there, we have a map of kind of the general transmission pipelines across the US. And on the right, it's a map of the general acidity of the soil types across the US. So you can see how, in certain parts of the country, the pH will play different levels of influence on the corrosiveness for those pipelines that are buried. And much like resistivity, pH also has a number of different methodologies that can be used to measure it. And again, none of these is necessarily better than another. It just depends on what your goals are for obtaining the measurement. The visual method is one of the most common that people are familiar with because, starting in elementary school, we do science experiments where we're checking the pH of various materials, and we've got the nice little litmus paper to check that. It's a very inexpensive way to check this. It's best suited for fluids as opposed to soil in our case. Then there's the photometric method, where a spectrophotometer is being used to measure wavelengths of light that can then be translated to the pH. This is typically not used for soil resistivity, but is used in lab settings for measuring pH of other types of materials. The method that's most commonly used for soil is the potentiometric method, and in this case, you have kind of an electrochemical reaction that's happening, and you're measuring the pH based upon the electrochemical reaction of a couple of different materials. And I'll go through a couple of methods for doing that. This is much like resistivity. This is what I would call a lab accurate. There's a lab accurate method for resistivity. There's also one for soil pH. And in this case, you have this potassium chloride solution, and you have kind of a wire assembly. This is great for getting those lab accurate measurements. The reason why this one is not particularly useful out in the field is because its whole assembly is contained inside of a glass container. And the moment you go and jab something like this in the ground, you're going to shatter it. So this is good if you wanted to bring samples back into a lab, like you would for soil resistivity if you were doing a soil box measurement, but not so useful for doing field measurements. And for this type of measurement, you're going to be taking multiple samples for a given area and then averaging those out. And then you can also compare these measurements. The way that they know, okay, this is the pH of my material, is they compare those to standards, to references. They'll have a solution that's a pH of 4, 5, and you can compare the reading that you're getting to those standards and know, okay, this is the pH that my material has. The more field accurate measurement is what we're going to be using most often in the corrosion industry. And the picture there, you may notice, or you may be familiar with that device. This is an antimony reference along with a copper sulfate reference electrode. And these two materials are most commonly used for measuring kind of that delta potential. Basically, a voltage is generated when you put these two reference materials in the soil. A voltage potential is generated between those two reference materials, and that voltage can then be translated to a pH level. And again, you want to get multiple samples for a given area, just so you can get a general idea, and you can then average that out and track that over time. The SRM100A is a little bit different than this one in that it much like the resistivity, it pairs those reference electrodes all down here in the bottom of the probe. So you can jab this into the ground, and here we have a copper ring. This is serving the same purpose as the copper sulfate reference electrode, and then we have this antimony ring, and this is a special type of metal that reacts readily or responds readily to changes in pH of a material. And all that to kind of sum it up is, this is the SRM 100A that we've mentioned multiple times. This device, just to give you a sense of how large this is, and what this is doing is it's, two of these probe terminals are facilitating the resistivity measurement, and two of the materials in the probe are facilitating the pH measurement. And each of these probe terminals is separated by an insulator. And there's a lot of wiring that goes up into here, and then ultimately into this box that's doing all the calculations of resistivity and pH. And the resistivity range for this, you see, is 0 to 700 kiloohm centimeters. And this is going to cover the majority of soil conditions that you're going to experience across the US, across the world, really, for the influence of corrosion. And again, as a lab accurate instrument, the accuracy on the resistivity is going to be plus or minus 5%, and on your pH is going to be plus or minus a half of a standard unit for pH. And I've got a sample of the Bullhorn probe, the short probe, for the unit, but we also have a much longer probe, so that if you had to really kind of reach into a dig site, into a hole, and get that reading, we have a simpler method for doing that.
So we have a question.
Question: How long does it take to get a pH measurement value in the field?
That's a great question. This device, it's a matter of seconds to obtain a single reading, and that's for both the resistivity and the pH. It's got 3 buttons on it, pretty basic. It's got a power button, it's got an ohm centimeter button for taking the resistivity, and it's got a pH button. And you press either the resistivity or the pH button, and within a matter of seconds, you have your reading. And I think Ed mentioned it, but just wanted to reiterate that we've had for the longest time the SRM 100, and this is the SRM 100A. And you're hearing a lot in the world right now about supply chain issues and all. So one of the reasons why we did this revision was to account for parts that we could no longer acquire. They've gone obsolete. And so in the process of doing that, we also took the opportunity to improve the product some. And one of the biggest improvements that we made was adding a rechargeable battery into this with a port so that it can be recharged. Previously, the design had 4 AA batteries that would need to be replaced after they were used up. But even with the 4 AA batteries of the previous version, and the rechargeable battery in this is a very low power consumption device, and so the frequency that you'll need to recharge this is not very high, just given the power consumption of the device. I think that may be all. I'm trying to find my clicker here. I think that may be all I've got here. So, do we have any other questions?
Do you need to make a calibration prior to a pH measurement?
Not immediately prior to that measurement, but this device, much like our digital voltmeters, is a device that we offer calibration service for. So you would send it back to us on an annual basis and get it calibrated, much like our DVMs, to ensure that it's operating still in its within its specifications.
Great. There's a little bit longer question, Andrew, that
Yep.
I think we're about 20 seconds away from being out of time. So I would ask you to follow up directly with Brad on that
Sure.
question, just to make sure it gets answered. I think it's a really good question. We're just kind of out of time. So
Sure.
thank you.
Happy to do that.
Thank you, Andrew, for presenting, and thank you, everybody, for participating. I'm sorry we didn't get to that last question, but as I said, Andrew will certainly follow up. So everybody have a great day, and we will see you in a month. Okay, thank you.
Thanks, everyone.
Bye.